All right, hearing none. What I wanted to do today, I'm not going to do today. I wanted to do some work with Microsoft Excel, but since the homework was extended by a week, I'm going to direct everyone to watch the Excel videos that I've posted on CourseLink. Go through those demos. Definitely do those over the weekend. That will show you step by step, because that's exactly what I would do right now if I were to go through an Excel demo. So go through those videos before next week, and I will go over that in class. But I do want to continue kind of speed up the coverage, if you will, not too fast, but fast enough to continue our discussions. Okay, so let me hide the presenter view. What I left off, I'm just throwing this all up here right now. This was the last thing I had left off with. Let me just put this here. Okay, so this is the normal distribution. This is a theoretical distribution of how a very large number of scores, we usually talk about a population, very large group of scores, and if you were to lay out all the values, this is what it would look like. You'd have some really small values, some really large values, but not a lot of those. And that's what you see in the tails. And then you would have the vast majority of the scores clumped in the middle like this. So that's the normal distribution. But these distributions take on different shapes. And this is what we call kurtosis. So kurtosis is actually a statistical value. I don't think we're going to calculate it in this course, but it's still early. But regardless, you can generate a statistical value for what's called kurtosis. So you take a look at the normal distribution, that theoretical distribution, how a very large number of scores will spread out. But what if that central cluster of scores, where most of the scores, what if it's a lot more narrow and the tails are really extended? Or instead of having that central cluster where you see it, it's more spread out. That's kurtosis. So it refers to the shape of the normal distribution, or the shape of the distribution in a vertical sense. It's still symmetrical. So I don't have the line on the screen, but if you imagine that line, that line of symmetry that cuts it into mirror images, the right and left, it's still there. I just forgot to put it on the slide, but I want to talk about the shapes for a moment. So there are three types of kurtosis shapes. Leptokurtic is the blue, and the leptokurtic has a more narrow shape to it. So the tails are longer, but those central cluster of scores, they're just even tighter around the line of symmetry. And those are the positive. And if you were to calculate it, and like I said, I'm not sure if we'll go through how to calculate it, but it's still early. It would be a positive number. So you would get a number for that. And if the number is positive, it would indicate a more narrow curve. Okay, but it's still symmetrical. It's still symmetrical. The mesokurtic, that's in the middle of the leptokurtic and the other one I'm going to show you here in a second. That's your normal distribution. So the normal distribution is a mesokurtic shape. Its kurtosis value is 0. So 0 in this case does not mean no shape. It's just a reference point, which is the normal distribution. Remember, there's only one normal distribution. Now, if you spread the scores out in the red, as you can see there, that's platykurtic. It means flat, so it's much flatter. And the value for that would be a negative statistic. I haven't gone through how to calculate it, but it would be a negative value, indicating that the scores are not quite as clustered, or the majority of scores are not quite as clustered around the line of symmetry. Okay, so make sure you draw that line of symmetry down the middle that cuts right through the peak. And even, well, you know what? I'm going to take my own advice. How's that sound? Let's give it some weight so you can see it. And good enough. Okay. Okay, so there's your line of symmetry. It cuts through the peak, and the right side is identical to the left side. The only thing is that the shapes are off or are different vertically. That's kurtosis. And I got to flicker the screen one more time. Hang on a moment. Technology was supposed to make things faster. It seems to be moving slower. Okay, so that's the vertical change in the distribution. But what if you have scores that instead of deviating, or instead of a change in the deviation vertically, the shape vertically, what about horizontally? That's what you have here. So this is what we call skewed distributions. The data, the scores, are skewed in one direction or the other. And so a skewed distribution is one that has a very pronounced tail, very long tail, as you can see in this one. So it still represents the same thing, that the majority of scores are clustered around here, wherever you see a higher curve. Now, the y-axis, okay, I'll put the symbol on the y-axis shortly. But you're still counting. That's frequency, but the symbol will pop up here in a moment. So you see this very, very long tail. Ignore the number 3 for now. That's part of the example. So right now, you have the central cluster of scores. This is an example I use all the time. So if our variable of interest is running speed, right? So this is a track and field kind of thing. So it's running speed. And if this is running speed for an Olympic event, we see that the speed is skewed or negatively skewed. Why do we call this negatively skewed? Look where the very long tail is. If the direction that the tail is headed, that's indicates the direction of the skew. So that tail is headed in the negative direction along the x-axis. So that's not why it's called negatively skewed. I'll tell you why, but that's what you would call it. That's a sign to indicate that it's skewed in the negative direction. And a couple slides, we'll find out the true reason. So a negatively skewed distribution shows that there's a relatively low number of extremely low scores. Remember, your key outcome variable, your dependent variable, is on the x-axis. So the example, as I said here, the 800 meters at the Olympic Games, running speed is a good example here. If you're not familiar with the 800 meters, it's 2 laps of a track. And the person that ends up winning is the one that achieves the highest average ground speed all the way through. So whoever can sustain the highest average foot speed all the way through is going to win. Now, what you see here is that you have the majority of the runners at the Olympic Games clustered around this region right here. Why do you have so many runners that are clustered around with the same apparent running speed? It's because of what's called an Olympic standard. So if you want to run in the Olympic Games, you can't just fill out the form and go. It doesn't work that way. You have to meet the Olympic standard to qualify for it. And so you have a lot of runners that have that qualifying speed. Okay, so very long tail heading in the negative direction, so we say it's negatively skewed. But there's a tail on the positive side too. This very subtle, very small tail up there. And if you follow this very high value for running speed and isolate this small cluster of runners, you'd see that there are 3 runners. So very high average running speed, but there's only 3 runners that have that very high speed. Those are the 3 Olympic medalists. So the top 3 that have that highest dependent value will have a low value on the y-axis. So always interpret this as you would any other graph. You start reading from the x-axis, follow the curve, and you see that the largest number of runners are at this particular speed wherever it hits the x-axis. Okay, so that's negatively skewed. Positively skewed, an example of positively skewed is household income. So same idea. Wherever that really long tail is, that tail, if you follow it, it's going in the positive x direction. You call it positively skewed. And so once again, skewness is the degree of asymmetry. It's the degree of asymmetry, with the normal distribution being perfectly symmetrical. Oh, okay. So household income is an example of something that's positively skewed, and we'll see why. What that means is that there's a relatively low number of extremely high scores. And so we're talking about high levels of household income. So household income is the example here. And where are the vast majority of household income values? Well, it's clustered wherever you see the curve achieving these high points along the y-axis. Once again, here's F for frequency. That's how many. How many households are at this particular household value, this particular household value, so on and so forth. Okay, so now let's isolate this part of the curve. Okay, so remember, now we're moving to the right on the x-axis, and now we're seeing higher household incomes. These are your millionaires. So this is annual household income, not how much money somebody has. This is annual household income. In the millionaire category, that value would be to the right. Now, if you follow that to the y-axis, that point on the curve, read the value on the y-axis, right? It's a low value. So because we're counting how many households relative to the vast majority, there aren't that many. There are not that many households with millionaire level annual incomes. Okay. What about out here? Keep following the tail, keep following the x-axis out to the right. What are you looking at here? You're looking at higher and higher and higher household incomes. We're going to put these in the billionaire category. So now we're looking at households that are on the order of billions of dollars in revenue, income per year. And the income can come from a lot of different sources, right? So it's not just salary. And you follow that curve, or you follow wherever the curve intersects, all the way to the y-axis, and what do we conclude? There are less billionaires than there are millionaires. And there are less millionaires than the vast majority of people from which this sample was obtained. And that is something positively skewed. Now, when we get to the statistics of this, you're going to see why we call it skewed. Okay. Questions on that? Questions? Okay, so now let's get to the 3 M's, right? The 3 M's, right? The measures of central tendency. The first one is the mode, and by definition, the mode is the most frequent. Do I have that up here? Did I define the mode before? I want to make sure. Oh, I did. Okay, let me define it again. The most frequently occurring score, and the one that shows up the most, that's your mode. So if you have a distribution of scores, and all those scores have different values, but 2 values are identical, that's your mode. Not the number 2, but the actual value of the dependent variable. So when we ask for the mean, the median, and the mode, it's not the reading on the y-axis, you're using the y-axis to guide the reading along the x-axis. Because what's really important is the outcome variable, right? That's really what we want to calculate. So now, as a descriptive statistic, when is the mode used? Typically, if your scale is nominal or ordinal, the mode becomes the descriptive statistic of interest. Case in point, how many students are majoring in psychology, history, mathematics, biology, chemistry at the University of Guelph and other departments? There's no inherent value to that. Our outcome measure of interest is how many students are registered in each of those majors. So there's no inherent value, there's no natural order to it, where it's just purely categorical. The descriptive statistic of interest would be the department, the major, that had the highest number, right? So the department with the highest number, let's say psychology, because it has 3,000 students majoring in psychology at the University of Guelph. I don't know if that's the actual number. You can go and look up that number. I think you can on the website. But the most commonly occurring score is the one you go with. And so the outcome measure is that number for psychology. And that's the key descriptive statistic. Now, there are limitations in using the mode as a descriptive statistic. Remember, just because you have a descriptive statistic, you have to be able to interpret what does that, remember, the number is just a number. We're using numbers to derive meaning from something. So if a distribution has more than two modes, which is possible, it starts to become difficult to describe the data, to interpret the data. Now, here's a unique distribution. So f of x, don't worry about that. Don't worry about the values along the x-axis, but this is a rectangular distribution. So negative a to a, those are just variable placeholders. Remember, just as a review, this is the range of scores. The x-axis is your outcome variable. Your x-axis so let me put this down here. Well, okay, close enough. I think you know what I'm talking about here. So there's your x-axis. That's the dependent variable. And copy, paste. As a review, hang on. I'm getting there. As a review, what did we call that distance? It's a range, right? The lowest possible score and the highest score you have in a distribution. So that's your range, there to there. Now, what is the y-axis calculating? It's how many scores you have, right? From here to here to here to here to here, all the way through at each point, and you see that you have an equal number of scores. Each outcome of your dependent variable. That's called a rectangular distribution. It's not good, it's not bad, it's just what the data gives you, except that using the mode becomes a little bit more difficult to interpret meaningfulness from it. Imagine this. So if we wanted to use the mode to describe the number of majors or the number of students in each department at the University of Guelph, this would be the equivalent of saying each department has 2,000 majors in that particular program. Equal number across the board. What does it mean? It just means that there's an equal number in each department. That's your descriptive statistic. So you might not be able to interpret that or apply that in any unique way, or you might, I don't know, administrators do that. But once again, that's why we generate numbers, is to get a clear picture of some observation. That if you just say, how many students are in psych? Oh, I think half the students at the university, because my classes are big in psychology. It may not be accurate, right? I wouldn't know until we actually collect the data. Little flicker again. All right, here we go. There we go. Okay. So these are the possible outcome values. Rectangular distribution, many modes, becomes tough to examine. Bimodal distribution, so the mode most frequently occurring score. This is a bimodal distribution. Once again, our X represents our outcome variable. You have the full range. This is not rectangular, but you see that we now have two modes. Exam results from whatever. So you have an exam, 200 students take it. Is it possible to have more than two averages? No. One average will be calculated. What about the median? Is it possible? No, you will have one median. Is it possible to have two modes? Yes, it is. So remember, modes refer to how many are occurring at a particular score. And that's what we see here. So sometimes bimodal distributions can be interpreted. So we give the midterm exam in this course, and we find that we have a large number of students that scored. Okay, let's start to the right. So we have a large number of students that scored. What's a desirable? I don't say good, right? I don't know what good means anymore. A desirable score on an exam out of 100%. What's a desirable exam score? Realistically desirable. So let's bring it up a little bit more. I'm going to split the difference. I'm going to go with 78. Okay, let's go with. I don't set exam. I don't have any expectations for averages in this course. So let's suppose we have a cluster of students where the most commonly occurring score is 78%. All right, so that's 78%. And then you get this drop off in terms of how many students scored less than that and greater than that. But you have some, but it drops off very quickly. And then what's a not so desirable score on an exam? Let's make the example a little more extreme. Less desirable. 40. Okay, yeah, I'm going to guess that 40% is probably not a desirable score. Okay, arguments like that's not reality here. But if we have 78, whole bunch of students, large number of students at 78, large number of students at 40, there is a pattern there. And as the instructor, I would look at that and say, that's weird. That is entirely strange. Now, either a lot of those students were absent the day I taught something unique, or there's something strange going on. So that's where, with a bimodal distribution, it's possible to make that interpretation. With a rectangular, I'm not sure how I would interpret something like that in terms of exam results. Yeah, that would almost be random spattering of exam scores. Yeah.
What's another like real life application for the bimodal? Because I think like for like sports and stuff like that, like right? Like I feel like I didn't usually like go.
I was thinking about this today. I was communicating with a guy, a friend of mine who works at the bank, and we exchange stories all the time. And it's a political example. Okay, we're dealing with politics here, not Canadian politics, politics of our friends to the immediate south of us. So I read an article today, 2 days old, that in the city of Las Vegas, Vegas, right, the city that never sleeps, Sin City, what happens in Vegas stays in Vegas. Um, there seems to be a marketing strategy for that city. The marketing strategy is that casinos, entertainment venues, and restaurant, all that stuff, all the shows, they're targeting affluent visitors. Affluent visitors, those are your millionaires. Those are the ones, those Vegas calls them whales. You know what a whale, you ever heard of a whale? Okay, a whale is somebody that has millions of dollars, tens of thousands, maybe hundreds of thousands of dollars to lose on one hand at the blackjack table. Okay, that's what the casinos call whales. They want to bring the whales in. But their marketing strategy is after affluent visitors because the middle income visitors are dropping off because costs are going up, individual costs are going up, and so now you see people that would normally reside in the middle class dropping lower. Basically, what's happening is the rich are getting richer, the poor are getting, and the poor are getting poorer, and there's more poor. So that would be bimodal. If you have the rich people, they're collecting more, those numbers are going up, and the poor numbers are going up. It might not be equal, but clearly bimodal. That would be the difference. Okay, so a little bit of economics, a little bit of politics. Let's move on because politics is fun to talk, but then we start to argue and things get unfriendly. But let's stay friends and let's talk about statistics. Okay, that's the beauty of statistics, right? You can't argue about statistics, right? We have no choice to agree but to agree because that's what the number is. Okay, so that's the mode. The median is the middle. And so the median, when you think about these three numbers, it's always a number on the dependent variable. We're using these other ways to find that measure of central tendency. So the median it's the middle. So it's the score at the 50th percentile. And I'll define it a little bit more specifically. It has to do with the actual curve. Now, the median score as a descriptive statistic does have some advantages. Um, as we just saw, the mode, you can have lots of mode, bimodal or rectangular, where every score, almost every outcome has a mode. But the median, you can only have one. So there's one descriptive statistic for the middle score. Okay, you can also refer to it as the middle score. So that's a clear advantage, right? That's good. Usually the median will be around where most of the scores are distributed. So that's another clear advantage, and we'll see that depicted on these two clearly different distributions. Aha, this is the big one here, number 3, outliers. An outlier is a score. So when I use the word score, I'm talking about your dependent variable, your outcome variable. So if we're talking about exam, it's an exam score. It's a score that sits far away from the central cluster of scores. So if we have a class average on a midterm exam that's, let's say, 62%. I don't think I've ever had a class average of 62%, by the way, but let's say 62%. But there's one or two scores in the high 90s, right? Where the vast majority of students are around that 62 mark. You can just clearly see it in the distribution. Then you got these two scores out here. The median statistic will not be affected by those outlier scores, and we'll take a look at a demo mathematically shortly. The average value is very affected by outliers. So which is interesting because whether it's exam scores or any other way to describe data, the average is the most commonly used descriptive statistic, right? What's the class average? What you want to ask is, what is the class median? Because the median is not, that value is not going to be affected by outliers. Okay, so the median is used for nominal and ordinal scores and skewed distributions. So if you're talking about a skewed distribution, the median becomes more of a stable descriptive statistic. So let's take a look at our normal distribution. All right. So where is the most commonly occurring score on the x-axis? Well, it's wherever the peak is. And this is unimodal, right? It's your normal distribution, it has one peak. And it's the one that has the highest value on the y-axis. Okay, we're good there. Now, what's the score of our outcome here that splits the distribution in half? Well, it's the middle line, right? It's the one that creates that mirror image in a normal distribution. And that's where the average is as well. So the beauty of a normal distribution, if, and write down capital letters with a big circle around it, if real data looks normal, which it won't. It can look close to normal, but it won't look perfectly normal. Those three measures will be at the same outcome value. All right, so that's the beauty of the normal. So this is the one, so this is a mirror image of the one on the right. All right, there's our positively skewed distribution. So this is actually more realistic when you're collecting real data. When you're doing research, whether it's in an academic setting, whether you're working in some other field where you're collecting numbers, even for quality control purposes, not because you want to publish a paper, but you're quantifying something and you're collecting it, it's not uncommon to have skewed data. Remember, if it's positively skewed, we have a small number of very high scores. All right, where's your mode in this? You don't have it on the notes, right? Okay. Let's give you about 10 seconds, 15 seconds, and on your notes, find the mode. You don't have a number because I didn't give you numbers, but just graphically find the mode on your notes, and I'll pull up the answer here in a moment. You don't want me giving you everything, do you? Yeah. Oh, you're answering the question. Oh, I don't know. I need you to draw it. You have to draw on your notes where you think it is. Pretend it's an exam. Pretend you're taking the midterm exam. I think the midterm exam is all multiple choice. I think. I don't know. This sounds like a good question to put on the midterm exam, doesn't it? You feel free to make suggestions. No, it doesn't mean you have to take them. Okay, there's your mode, right? You find the highest point on any distribution. It could be normal. It could be much flatter, but you're looking for the high point, right? The high point that has the highest value on the y-axis, and then you beeline that down to the x-axis, circle the x-axis number, and that's the mode. Now, the homework, question number 2, I think I gave you 10 scores, 11 scores, something like that, the lengths, baby lengths or something like that. 10 scores? Okay, so 10 scores, you can look at the numbers, right? And you can identify the mode. But what if you got 1,000 scores? Then you just can't look at the numbers, right? You need some other way to do that. Okay, so that's the mode. What am I going to put up next? Where do you think the average would sit? If you had to find the average of your outcome variable on the x-axis, where would you find it? I'll give you a hint. When you have a skewed distribution, right? So to the left, those 3 M's are not the 3 M's superimposed anymore. All 3 separate. All 3 separate when you have a skewed distribution. That's why researchers, when their data becomes skewed, they start, they get they feel like they're getting acid reflux. Their heart rate goes up. They get a little bit down in the dumps because the data is not behaving in the way they want to. Too bad. Those are the data. What are you going to do? That's life. Okay, so there's your average. Now, okay, so the average is always going to sit on the side of the long tail from the mode. You won't find the average on the other side in a skewed distribution. So if this was negatively skewed, the mean would be on the left side of the mode. So the mean is always on that really long tail in a skewed distribution. What's missing? We got one more M, the median. Where is it? I'll give you a hint. Another word for median is what? Middle. That's my hint to you. So go ahead and identify where you think the middle score is with respect to the two M's we've already put up there. Let's do it. Okay. Right? It's in the middle of these two. Now, that's not why it's called median, but that's a handy way to remember it, where in a skewed distribution, the median is in the middle, somewhere between the mode and the average. Questions? Questions? Okay. Are you ready for the real reason we call this positively skewed? The real reason is take a look at the average. So the average was in a normal distribution, the average was sitting on top of the mean, was right there. They were all superimposed. When you positively skew the distribution, the average is skewed in the positive numerical direction. So skewed distributions have the effect of skewing an average. So those small number of millionaire and billionaire values, right? You might only have 5 of them in the province, 5 billionaires and maybe 100 millionaires on top of the millions of people in the province. But those few have such a high number of the outcome that it actually impacts the average salary or the average household income. That's why the average in skewed distributions becomes a less stable statistic. Those millionaire and billionaire values on the x-axis, only a few of them, will not skew the median. The median is always defined as the middle score. Really pull the average. Okay, so now you got some numbers and you want to calculate the median. And how do we do that? So I'm just going to focus on a small sample here, a small number of non-continuous data. Non-continuous data means that there's no fractions, right? Whole numbers only. Okay, so you only got whole numbers. Now here's an example. So the median score is the middle score. So the way you, okay, so you order the numbers and just use the natural way to order numbers from low to high. Okay. If you went high to low, makes no difference. But I always say just follow the natural order of numbers, left to right. These are just 5 random numbers. Which one's in the middle? Whichever one is the middle score. You have an even number. You have an equal number of scores to the right, equal number of scores to the left. My right, your left. My left, your right. Right, because we're mirror images here. Okay, so what is your median statistic? It's 18, not 3 from the left. It's 18, and that's what you would use. Okay. I'm pivoting back to slide 22 in a moment, but I want to just finish up slide 23. Now you have an even number of scores. The median is still the median. It's a location identification. So we have 4, 4, 9, 11, 12, 14. Where is the physical middle of this distribution. Don't be fooled by the numbers, right? It's a location. It's right there. That's the middle. That splits it into equal right and left. There's nothing there. So what's your median? Yeah. You guessing? Okay. Just cut the numbers and just meet it in the middle. Whatever number you have on the right and the left, cut it in half, which is to say you take the average between those two numbers. So it's 9 plus 11, divide that by 2, and that puts you smack dab in the middle. So your median, this is where it might get a little bit confusing, your median value is 10, but if you look at your raw data, you don't have a 10 in there. But that's okay, because we're calculating a descriptive statistic. Whether it's a mean, median, mode, the descriptive statistic, especially with the median and the mean, may not be that precise value in your data set. It's just one number. If you had to take a picture of one number and look at something that describes it, it's the median or the mean. Or if you got nominal, ordinal data, it would be your mode. So the beauty of the median, it provides magnitude and location description of a set of data. So I hope you have your calculator with you. These classes are too short. I wonder if I can put in a request to make these lectures like 70 minutes. That would be really great. If I could have 20 more minutes 3 days a week, wouldn't that be awesome? 20 more minutes of me? I would have a great time 20 more minutes with you, but anyhow, okay. I want to do a demonstration of the mean and the median. My calculator. What I would like you to do right now, and I'll do this with you, is calculate the average. So you're going to add up all the numbers and you're going to divide it by 5. So add up all the numbers, divide it by 5. I'll do that right here. So I want to work quickly. 11 plus 13 plus 18 plus 19 plus 20. I'm going fast. Divided by 5. Okay. I got 16.2. I got 16.2 as an average. Okay, so what we say now is that the average of right here, okay, so the average right here of this score, that's kind of small there. Let me bring this up to 22. There we go. Is 16.2. I'm going to move this out of the way. Okay. Hang on. Okay. Okay, so our average is 16.2. If I'm going too fast for you, not to worry, this is getting recorded. You can always go back and you can listen to this and watch this all the time. Okay, so two separate situations. So our average is 16.2, our median is 18. New set of data. Ready? Ready for it? Okay. Calculate the average. So you add up the numbers, divide it by how many numbers you got. Follow the process. Okay. So the average down here, I got 52.2. I got 52.2. Okay. There's your median. The median is still the middle score. How many scores you have? You find the one that's located right in the middle. So what we've seen here in these two examples, the median score is still 18, right? That hasn't changed. But what did changing 20 to 200 do? Completely skewed the average in the direction of the 200. Now, if you're dealing with real data, and this might represent home values, the price of homes in a neighborhood, what's the average price of homes in a neighborhood? If it's $1 million or $1.1 million, but at the end of the block, you got a $5 million mansion among 10 homes, that's skewing the value upwards if you're just looking at the average. A more realistic statistic would be the median price of the household, because that $5 million mansion value is not skewing the median value. It becomes a more stable statistic, better reflection of home prices in that neighborhood. So this shows you where the advantage is sometimes in using the median. Look at those numbers, 11, 13, 18, 19, 200. That's an outlier, right? 200 is a major outlier there. It is so different than those other scores, but look at the influence it has on the average. Median does this, big deal. I'm not changing. I'm still the middle score. So median, very helpful. And there is your average. In statistics, we call it the mean. In statistics, we call it the mean. I got one more minute. I'm just going to do this one slide, and we'll kick it here. So the mean, the average, most commonly used statistic. Now, even with skewed distributions, when we deal with large numbers, the average is still most commonly used one, and that does provide some limitations. So it's the mathematical center, not the middle score. The middle score is the median. The mathematical center is a different distribution. It's a balance point, and I'll do it. Yeah, I guess I'll have to wait till Monday to do a demo. And there's your equation to calculate the mean. What's that funny looking symbol in your numerator before the x? In the numerator, the x, that symbol before the x? What's that? Who was here on Wednesday? Are you asking me or telling me? You're telling me. Yeah, the summation notation. You see what I'm talking about? You can't get away from summation notation. Really pay attention to question one. Go over the video if you have to, because from this point forward, summation notation will appear in your dreams. You will dream summation notation, and you'll wake up in a cold sweat. Like, I'm at home. Why should I be? I'm in statistics. Okay. Anyways, I thought that was funny. Have a great weekend. We'll see you on Monday, and think statistics.